For centuries, a ghost has haunted the workshops of the world's most brilliant inventors. It is the specter of a machine that, once started, runs forever. A clock that winds itself. A wheel that pumps its own water. An engine that fuels its own fire. From the 13th century notebooks of Villard de Honnecourt, with his sketches of an overbalanced wheel, to the elegant, self-flowing flasks proposed by the great natural philosopher Robert Boyle, the dream of perpetual motion has been one of humanity's most persistent and seductive pursuits. The promise is irresistible, a source of infinite, free energy that could power cities, carry us to the stars, and shatter the limits of our civilization. Yet, every single attempt, without exception, has failed. Not from a lack of genius, not from shoddy materials, but from a confrontation with a cosmic law so fundamental it operates as the universe's silent veto. This isn't a story of engineering failure. It's the story of a fundamental truth about reality itself. To understand the depth of this impossibility, we must first distinguish between the two classes of these forbidden devices. The first, a perpetual motion machine of the first kind, is the more brazen offender. It's a machine that purports to create energy from nothing. A closed box that gets hotter without any fuel. A motor that spins faster and faster, generating more power than it consumes. This type of machine directly violates a law you likely learned in high school, the first law of thermodynamics, also known as the law of conservation of energy. As articulated by pioneers like Julius Robert von Mayer and James Prescott Joule in the mid-19th century, this law is an ironclad statement of cosmic accounting. It declares that energy cannot be created or destroyed. It can only change form. The chemical energy in a log of wood can be converted into thermal energy and electromagnetic energy when it burns. The potential energy of water held behind a dam is converted into kinetic energy as it falls, which is then converted into electrical energy by a turbine. The total amount of energy in a closed system, the universe itself being the ultimate closed system, is constant. It's a zero-sum game. You can't get more out than you put in. This law is so foundational that the U.S. Patent and Trademark Office has, for over a century, refused to even examine applications for perpetual motion devices without a working model. A quiet, bureaucratic acknowledgement that this is a dead end. But this is where the real mystery begins. The first law, in its elegant simplicity, seems to leave a loophole. If energy is never truly lost, only transformed, then why can't we just build a machine that perfectly recycles it? This is the dream of the perpetual motion machine of the second kind. This machine doesn't claim to create energy from nothing. It merely proposes to use it, capture it, and reuse it in a perfect, frictionless, eternal loop. Imagine a hyper-efficient steam engine. You burn fuel to boil water, the steam drives a piston, the piston turns a wheel. The first law is satisfied. But what about the heat that radiates from the engine, the sound of its churning, the friction in its gears? That is all energy too. Why can't we build a device to capture that waste heat, convert it back into mechanical energy, and use it to power the engine indefinitely? The energy is all there, just in a different form. It's like a perfect financial system where every dollar spent is immediately returned to your account to be spent again. It seems logically sound, a problem of clever engineering rather than a violation of physics. Proponents argued that with perfect insulation, frictionless materials, and flawless energy conversion, such a machine was theoretically possible. What invisible force, what cosmic tax, prevents this perfect cycle? If energy is conserved, why can't we simply recycle it endlessly, achieving the dream of perpetual motion? From that tantalizing question of recycled energy emerges the universe's most profound and unforgiving answer. The reason perpetual motion is impossible lies not in the quantity of energy, which is conserved, but in its quality, which is not. There is a cosmic seam woven into the fabric of reality, a fundamental asymmetry that dictates the flow of events. This is the second law of thermodynamics, and its silent, unyielding agent is a concept known as entropy. Stated formally by the German physicist Rudolf Clausius in 1850, the law declares that in any isolated system, the total entropy will always increase or, at best, stay the same. It never, ever goes down. But what is entropy? The common shorthand is disorder, but its true meaning is far more subtle and powerful. Think of your desk. A clean, organized desk is a state of low entropy. There are relatively few ways for your books, papers, and pens to be arranged in a tidy configuration. Now imagine scattering them randomly. This is a high entropy state. There are vastly more ways for the items to be arranged in a messy configuration. The universe, on a statistical level, simply favors the states that are more probable. Disorder is easy, order is hard. The Austrian physicist Ludwig Boltzmann gave us the deepest insight into this with his work in statistical mechanics in the late 19th century. He connected entropy to the number of possible microscopic arrangements or microstates of particles that result in the same overall macroscopic state. Imagine a box with a divider, gas molecules on one side and a vacuum on the other. This is a low entropy, ordered state. There is only one way for all the molecules to be on the left side. Now remove the divider. The gas expands to fill the entire box. This is a high entropy, disordered state. Why? Because there are an astronomical number of possible positions and velocities for the molecules when they are spread throughout the box, compared to the single arrangement where they are all huddled in one corner. The universe doesn't have a preference for messiness, it simply follows the path of highest probability. Disorder is easy, order is hard. The Austrian physicist Ludwig Boltzmann gave us the deepest insight into this with his work in statistical mechanics in the late 19th century. He connected entropy to the number of possible microscopic arrangements or microstates of particles that result in the same overall macroscopic state. Imagine a box with a divider, gas molecules on one side and a vacuum on the other. This is a low entropy, ordered state. There is only one way for all the molecules to be on the left side. Now remove the divider. The gas expands to fill the entire box. This is a high entropy, disordered state. Why? Because there are an astronomical number of positions and velocities for the molecules when they are spread throughout the box, compared to the single arrangement where they are all huddled in one corner. The universe doesn't have a preference for messiness, it simply follows the path of highest probability. The gas spreads out because it is statistically inevitable. This relentless increase in entropy is the cosmic tax on every energy transaction. When you burn fuel in an engine, the concentrated chemical energy is converted into useful work, but a significant portion is inevitably lost as waste heat. This heat dissipates into the surrounding environment, warming up air molecules and spreading out. The total energy is conserved, but it has been degraded from a concentrated useful form into a diffuse unusable form. You cannot spontaneously gather all those randomly moving warmed-up air molecules and concentrate their energy back into a high-temperature source to drive the engine again. It would be like expecting the scattered items on your desk to spontaneously leap back into their neat, ordered positions. It's not impossible in an absolute sense, but it is so statistically improbable that it would not happen in the entire age of the universe. This irreversible degradation of energy quality is what gives the cosmos its direction. It forges the arrow of time. Most fundamental laws of physics, from Newton's mechanics to Einstein's relativity, are time-symmetric. A video of planets orbiting a star would look just as valid if played in reverse. But the second law is different. It is a one-way street. You remember the past, not the future. An egg can be scrambled, but it cannot be unscrambled. A star radiates heat and light outward, it doesn't suck it back in. These are all manifestations of entropy on the rise. This law dictates the grand unfolding narrative of our universe. The cosmos began in an incredibly low entropy state at the Big Bang, a hot, dense, highly ordered configuration. Ever since, as it expands and cools, its total entropy has been increasing. Stars are magnificent temporary pockets of order, but they achieve this by burning through their fuel and massively increasing the entropy of the universe around them by radiating heat and light into the void. Life itself is a testament to this principle. An organism is a highly ordered low-entropy system, but it maintains this state only by consuming energy from its environment and expelling waste products and heat. We are temporary eddies of order in a cosmic river flowing inexorably towards disorder. The ultimate consequence of this law, as first proposed by scientists like Lord Kelvin, is the heat death of the universe. In the unimaginably distant future, all the stars will have burned out. Black holes will have evaporated. The universe will have expanded to a vast, cold, and dark expanse where all energy is spread perfectly evenly. A state of maximum entropy. A state of perfect equilibrium. In this final state, no temperature differences will exist. No energy gradients will be left to exploit, and therefore no work can be done. Nothing will happen, ever again. The second law is not a barrier to our ambition, but the very canvas on which reality is painted. It is the law that gives time its direction, life its struggle, and the cosmos its grand unfolding and ultimately finite story.